Let's start the seminar today. We have Flip clinched from the Seçkin. He's presenting a paper together with Bettina, Klaus, and Seçkin Özbilen. It's a Turkish name. I have some difficulties, so we can start. Feel free to start.
Okay, so thank you very much for the invitation. I'm happy to be here to present this work. So last week I visited Bettina and we worked on this topic and we obtained more results. I don't think I will have time to explain these results, but more or less the type of results are similar to the ones that I present today. So that gives you a good idea, you know, what we are working on. So let me see. So the title is very long. Let's start, with the hedonic coalition formation problem part. So this is the topic. So just to give you an informal introduction. So I'm not sure if you're familiar with this DAX tool seminar conference in Germany. It's held every year or every 2 years or so. So a group of researchers meet during a week, and it's a very boring place, which is actually very good, because then once you're together, well, you start talking about research or maybe some other things, but the idea is that people present and also start working on projects, so try to find possibly new co-authors. And one question then one can ask is, okay, how can we partition the participants into working groups? Okay, so who's going to work with whom and on what topic? So this is just an example of a so-called hedonic coalition formation problem, but there's also many other situations that require the formation of teams, social clubs, organizations, societies that are very similar. Okay, so 2 things. First of all, so this literature sort of started with the paper by Banerjee et al. And Bolomonaya and Jackson. And I also put here this Dres and Greenberg reference, because they sort of introduced this idea or the notion of hedonic coalition formation. So let me go back. So it says here, so coalition formation, but hedonic coalition formation, which simply means that you care actually only about the members of your own team. So in other words, I would like to work with Cory and Paco, and also Chichi, sorry. Let me include you as well, theory people. So, but then I do not care too much about how the other people are organized into teams, right? So, how macroeconomists or empirical researchers, how they organize themselves. I care about the people with whom I am, so that we can write good papers. Okay, so I may have preferences over theoretical researchers, let's say, right, over potential groups. And of course, I'm always I think about myself, about my own group. So I consider myself together with Paco, together with Cory, or with the 2 of them, or Chechu, or whatever. All these combinations I'm interested in, and then I want to, of course, to get the best possible coalition. Okay, so this is hedonic coalition formation, and 2 particular cases are the famous marriage and roommate problems. So marriage problems is simply, this is slightly, politically incorrect, but very simple classical situation where a group of men and a group of women, we want to match them. Men can only marry women, women can only marry men. So then the question is, okay, which couples can come out of this situation? More general roommate problems, it's a one-sided problem, and we want to match the agents in pairs, right? A roommate. We have to share a room. Okay, with whom can I best share this room? These are just 2 cases, but in general, the coalitions can be larger. And what we do in this paper is we want to study good outcomes, which we think, well, in this case, what we do is define good as core-stable partitions. Okay, I will explain later what all of this means. This is just very, vague summary. And what we do is we look at core-stable partitions. We want to study core-stable partitions for new types of situations, in other words, preference domains for which these good outcomes exist. And then the last item is to study mechanisms, so that systematically assign partitions to each possible problem or preference profile in a way that such that truth telling is a weakly dominant strategy. In other words, a strategy-proof mechanism. Okay, and I will come back to that later. There's lots of literature, but let's not go into this. For that you can read the paper. There's also some nice reviews where the stability concepts are all mentioned and how they fit together. Also regarding strategy-proofness, there's literature, of course. We are not the first ones to look at these concepts. And then there's two closely related papers, Akal-Revilla and Dimitrov and Sang. I will come back to these papers later. They have a similar sort of paper, similar results on another domain called top responsive preferences. Alright, so let's go into the model. It's super simple, incredibly simple. It's a set of agents N, and we define a coalition as a non-empty subset of this set of agents. And each agent is interested, in being part of some coalition. And so each agent has preferences over this calligraphic Ci, so all the sets S of which agent I is a member. Okay, so I rank them. The preference relation is complete and transitive, but there could be indifferences. I could be indifferent between two different coalitions. Okay, we do not exclude that. Just some notation, preference profile, this squiggle. Hedonic game is then a pair given by the set of agents N and the squiggle, or since we fix most of the time, it's actually just about the squiggle thingy. And an outcome, as I mentioned at the beginning, is a partition of the set of agents. Okay, so very simple preference relations over coalitions, and then an outcome is a partition. Okay, some more notation, pi for partition and pi I for agent I's coalition. Okay, so now, so of course, this is super general thing, and many things can go wrong. There's a large literature about this problem. If I do not make any assumptions on the preferences, the core will be empty, things will go terribly wrong, and people have studied certain preference domains. So what we do in this paper, this is not an exception, we look at a particular preference domain, which is the following. So let me explain how it works. So take any preferences of agent I. What we will assume is that, I'm an agent I, and now I compare working on my own on a paper, and I compare that, with working with, let's say, Paco. Okay, so Paco is agent J, and I compare these two situations, and what we impose is this condition, that I'm not indifferent. Either I think, working with Paco is a good thing, or it's a bad thing. Okay, so what we can do is we can split the set of agents of the other agents into two sets. Friends and enemies. So a friend, if working with that agent J, is better than working on my own, and enemy if it's worse. Of course, this terminology is not very nice, friends and enemies, it's, but at least you get the idea, okay? So maybe you can think of productive, unproductive agents or whatever, but let's keep the notation and wording very simple, so friends and enemies. Okay, so this is one assumption, and there's some further simplification. It could also be that, Paco is my friend, but maybe Paco thinks, I'm an enemy. So we do not exclude that option, so it's not necessarily mutual. Okay, so this is the last line here. Okay, so apart from that, from splitting the set of agents into other agents, into friends and enemies, we make the following assumption. So this is really the the description of the preference domain. So what does it say? It says the following, two conditions. So adding only an enemy is bad. So I'm agent I, let's think of some coalition S of which I am part, and now let's consider adding this enemy E to the set. Okay, so S joining agent E, the enemy. This will make it worse. Okay, very simple. Second condition, adding a friend together with enemies is good. Okay, so now consider again agent I, the set S, and let's take some friend F and some subset E of enemies. Right, so this F, the small f, and the capital letter E, the set E, they are not yet in S. And I add both of them. I add the friend and the set of enemies. Then our condition is the following. Okay, it says the resulting coalition is better than the coalition S that I started with. Okay? Okay, don't start complaining, because I know this is a strong condition, because basically what it says, as long as I add some friend, independently of which other enemies I add, you know, the thing gets better. Okay, so this is a strong assumption, I agree, and I can come back to that later. There's a reason why we put this condition here. Okay. But one can maybe think of situations in which this is quite reasonable. Maybe another situation it's not. Okay, so I'm sorry for that. But we can try to weaken it, and I can talk about that later. So the main results are about these type of preferences. So here's an example. So imagine I'm agent 1. Okay, I'm agent 1, and my friend. So there are like 6 agents in total. So apart from me, there's agent 2, 3, 4, 5, and 6. And imagine that agent 2 and 3 are my friends. So 4, 5, and 6, they are enemies. Their preferences could look like this. So on the right hand side you see an example. So one thing that has to be very clear is, okay, if I fix a set of friends and a set of enemies, the preference relation can still be, you know, many different things. You know, it doesn't pin down the exact preference relation over all possible sets. Here's just an example. So start with the bold-faced set 1, 2, 4. I'm agent 1, and imagine that I'm with my friend 2 and an enemy 4. Okay, this is the bold-faced set. Then if I add an enemy, for instance agent 5, then I move down to the red set. Yes? But I could also move up to the blue set. How do I do this? Well, I add one friend, agent 3, and I add some enemies, namely 5 and 6. Okay, so then I move from the bold-faced to the blue set. Okay, this is just an illustration of the two conditions. Okay, it could look like this. Now, this is of course a restricted domain, but there's in fact 2 subdomains, and one of them has already been studied in the literature, namely this appreciation of friends by Dimitrov et al. What does this condition say? It says, well, it doesn't really care about the identity of the agents, it simply counts the number of friends and the number of enemies. So then, when I compare to coalitions of which I am part, if the number of friends is larger in this coalition than in this other one, then I prefer the first coalition. If it's the same number of friends, then I check how many enemies there are, and I want to minimize the number of enemies. Okay, so this is just, you know, just a cardinal condition, just checking the number of friends and enemies, which is a subdomain of our domain. And now there's another domain, which I will not talk about, another subdomain called lexicographically friend-oriented preferences, where we extend an agent's strict ranking over all individual agents in a lexicographical way. Basically, you know, I have a list, you know, this is my best friend, this is second best friend, the third best, whatever. And then if I compare two coalitions, what I do, I first check whether my best friend is there. If it's here but not there, then I prefer this set. If it's in both sets, then I go look whether the second best friend is in the two sets or not, and so on and so forth. I basically use the strict ranking over agents to generate a ranking over coalitions of which I am part. Okay, so here's just a very simple example. 4 agents, I'm agent 1, that's my friends are 2 and 3, and the enemy is agent 4. Then there are 13 preference relations that are friend-oriented. Some of them are strict, others are not. One of them is in this cardinal domain that I mentioned before, the counting domain. And then, okay, 2 of them are lexicographically friend-oriented. So here that's just an example, just to show you there's different preferences, some with indifferences, as you can see, some others not. There's variation. Let's not, go to exact details, just to show you that it's not completely determined, right? It's not we are not talking about a super small preference domain. Of course, I'm not sure how I will not quantify the size of the domain or anything, but I'm just saying, okay, this is not unique. There's still a lot of variation, even if I fix, the set of friends and enemies. Now, more importantly, the 2 papers that I mentioned before, they look at the domain of top responsiveness. So the condition is basically this. So what does it say? It says, okay, maybe this is these formulas are harder to read, so let me go through them. So condition A says for any potential set S, of which I am a member, so S contains I, then what I could do is I could look at the choice, so-called choice function, which what it does is, given set S, it takes the best coalition for agent I, that also includes I. So basically you construct a coalition with members from S, and that includes also agent I, and that is the best one according to squiggle I. Okay, simply I pick the best set from this set S, and I have to be there myself as well, of course. Okay, so this is just a normal choice operator, or whatever you want to call it. And the condition is that this set is unique. Okay, potentially, since there can be indifferences in the domains, potentially there can be more, I could, for instance, I could be indifferent between working with Paco and with Cory, for instance. Right? So it could be 2 choice sets that, if I look at, me, Paco, Cory, so we are 3 agents, then the best possible set could be working with Paco, or the other one working with Cory. And maybe the 3 of us together, maybe that's too much, maybe it's too many people. So the choice set then would be, 2 coalitions. So this condition says there's a unique maximal element. And then there's condition B, there's 2 sub-conditions. So condition 1 says the following. Take any coalitions S and S prime. Now I look at this choice set, let's call it the inner cycle, the bodies within S and the bodies within S prime, and I compare them. And I see, oh, right, I prefer the inner circle, the choice set of S, to the choice set of S prime. Then what Alcalde and Revilla impose, is that independently of all the other agents in S prime, there could be really bad agents, but they don't care, S should be still better than S prime. Okay, so this is a strong condition. Condition 2, so maybe I should give an example of this. So let me see. So here, for instance, the second column. So if I look at coalition if I look at coalition 1, 2, 4, I pick 1, 2, right? Look at the second column. If I have to choose between agents, so I'm agent 1, sorry, and if I can, if you tell me pick some subset of agents 2 and 4 and include myself, agent 1, then I prefer 1, 2 to 1 to 4, or being on my own, or being with 4 alone. Okay? Same thing for agent 3 and 4. If I have to pick between 3 and 4, what I do is I will pick only 3, not 4. I do not include 4. Now, 1, 2 is above 1, 3. The choice set 1, 2 is above the choice set 1, 3. But if I include 4, so now I look at the larger set from which I chose. If I include 4, then the order switches. I prefer 1, 3, 4 to 1, 2, 4. This is not allowed by this domain, because it says if the inner circle, if the choice set is better for S than for S prime, then S should also be strictly better than S prime, independently, of the other agents that are there and S and S prime. Okay? So our domain, as I pointed out, has strong conditions, but this is also, I think, a strong condition here, this B1. B2 says simply if the inner circle is the same, then a larger set is worse. So this S prime is a larger set in terms of inclusion than S. So larger set is worse. Think of the other agents that are not in the choice set as bad agents. So then adding more bad agents makes the set worse. So here we have that S is better than S prime. Okay, so I already explained that some of the friend-oriented preferences are not top responsive. I explained that they violate this B1. In general, this is the picture that we have of the domains, right? Top responsive preferences, friend-oriented preferences, and then there's these small subdomains that are part, in fact, of both domains. Okay, so this is the general idea. So we look in this paper, we look at friend-oriented preferences, right? Okay, so here's an example. So agent 1 has friend 2 and enemy 3, which means that the best possible set, maybe I should have said yes.
So, and then what's the reasoning behind the fact that when 4 is not included, I might prefer 2 over 3, but when 4 is included, then I prefer 3 over 2, right?
So, well, it might be the case that this agent 4 has, let's say, brings negative externalities to this other, if I'm working with Paco and then some other person comes in, maybe, there's not good cooperation, there's some problem between Paco and this other person, and while if I work with Cory, then maybe this other person, there's no conflict or any problem. So, I'm not saying that, this is what we should have, or what I'm saying is, okay, we do not exclude this kind of situation. So in our domain, we allow for this to happen, whereas in this other domain, necessarily says, independently of the identity of Mr. 4, if it's good for Paco, then it should also be good for Cory, and the other way around. Okay, so it's just more we allow for a richer domain in that sense. But of course, we make other restrictions, we have other assumptions. So one can criticize, let's say, criticize is too strong a word, but there's let's say restrictions in both domains in one way or another. Okay, so I was saying, so if I'm agent 1, the best friend, so my only friend is agent 2, so the best possible set that I can get is to be only with my friends, in this case only one friend, so the best set is 1, 2. Then adding enemy, which is agent 3, makes it worse, but this is still better than working on my own, being agent 1. Why? Because if I'm working on my own, and if I add agent 2, which is a friend, and I add also an enemy, as we saw by definition of friend-oriented preferences, this makes the set better, right? As soon as I add some friend, I improve. For agent 2, I have 2 friends, so agent 1 and 3, so then the best set is 1, 2, 3 for agent 2. And then one has to maybe make a choice to say, okay, which set do I prefer? 1, 2 or 2, 3? Or maybe I'm indifferent, right? So these are agents 1 and 3 are both friends, and our conditions do not specify, do not pin down, do not say, okay, then 1, 2 should be better than 1, 2 should be better than 2, 3, 2, 3 should be better than 1, 2, or the agent is indifferent. All 3 options, possibilities, are really possible with friend-oriented preferences. In this example, I chose to say, okay, let's pick 1, 2 better than 2, 3. But this is just a choice that I made. Of course, so the partitions are the possible outcomes, pi 1 up to pi 5, but okay, I just put them there just to have a complete picture. What we are interested in is in blocking, and specifically in the strict core. So what we want to avoid is the following. A partition is weakly blocked by a coalition if for each agent in this S, coalition S is better, weakly better than the proposed partition pi. Agents only compare the coalition of which they are part of. So agent I compares S with pi I. And what we want to avoid is that every agent I in S says, okay, well, I prefer to break off, I want to, let's ignore the proposed partition pi, let's form a group, let's form a coalition S, where we all are weakly better off, and some agent is strictly better off. Okay, this is what we call weak blocking. And then the strict core is simply the partitions that do not have this kind of weak blocking. Okay, standard definition. So this is just notation, SC, strict core. Now the good thing of strict core is that it implies, and I will not check that, but it implies also individual rationality and also Pareto efficiency. Okay. Now another thing you could do is say, well, look at blocking where everyone strictly improves. So a blocking or strict blocking is this: every agent in S strictly improves upon the partition, and then core stability means that there is no such strong or strict blocking. Okay, so this is the core or weak core. So this is some just notation to see. So since I exclude, since the blocking has to be stronger, right? More partitions are not vulnerable to the blocking because it becomes more difficult to block. So there's more partitions that will be allowed. So we naturally, extend the strict core to the core. Okay, this is a subset. Paco, you had a question?
No.
Okay.
S is not a partition, no? It's only
No, this is just notation. Sorry.
You compare coalitions with partitions.
No. I never. No. So I always compare. So here you see this S as a coalition. I compare it with pi I. Pi I is the coalition of which I am part in the partition pi.
Sorry, pi I is.
Pi I is notation. The I is the index that indicates the coalition of which agent I is part in partition pi.
Right.
Okay,
okay.
I never look at complete partitions. If I'm an agent, I'm interested in working with some people and here or there, and I just compare, and I don't care whether macroeconomist or whatever how they get into coalitions. Okay. Okay, so since there's little time, I will just mention this here. So, of course, it's important to check whether these concepts are really different, right? Because I can introduce all kinds of definitions, but maybe they boil down to the same thing, but that's not true. So the strict core is actually a different thing than the core. So in other words, the strict core can be a proper subset of the core. Okay, this is just a very simple example, but since there's little time, let me not go into this. So what I want to do, so this is good to know, these are different concepts, but now of course, maybe the more important question is existence, right? Do there exist core stable, or in fact, even better, strict core stable partitions? Okay, so how do we proceed? Okay, so think of any problem, friend-oriented preferences. In this case, there's 13 agents. Every agent has a set of friends, a set of enemies, and then, there could be, pretty wild, let's say, preference relations, even given this specific friends and enemies. But what I do is the following, very simple. So imagine I'm agent 1, and my only friend is agent 2. Then what I do is I point to agent 2. Okay? Now imagine I'm agent 2, and my friends are agents 5, 8, and 3. What I do is I point at my friends 5, 8, and 3. So all agents, what they do, they just point at their friends, independently, of how the specific preferences are. I only point at my friends. So there's very little information that I use from the preference relation, but let's use that. Then what I get is this so-called friendship graph. And I'm interested in, and you will see why in a minute, in the so-called strongly connected components. Okay, this is actually a very simple concept, but let me explain carefully. So look at agent 1 and 2. They are strongly connected. Why? Well, I can move from agent 1 to agent 2 via a path. Well, actually there's just one link, one edge. And I can move from agent 2 to agent 1 through some path. Again, very simple. Okay, directly. But okay, this could be more, could be larger path. So 1 and 2 is a set that is strongly connected, but it's not a strongly connected component because there's a larger set that is also strongly connected and that contains agent 1 and 2, namely the set 1, 2, 3. I can move from 1 to 2 and to 3. I can move from 2 to 1 and to 3, and from 3 to 1 and to 2. Everyone is connected, right? I can move through the graph and only pass through agents 1, 2, and 3 and connect all of them. I cannot extend this, I cannot include agent 5 because there's no path from agent 5 to agent 3, or from agent 5 to agent 1, or not even to agent 2. Okay, so what I get, you can see here, these will be the strongly connected components. Okay, so these are, it's so important. This is uniquely defined. So if you give me a friendship graph or any directed graph, these components, it's unique. This partition is unique. And it can be calculated, computed in polynomial time. There's no issues here. It's relatively simple to do. There's algorithms for that. Okay, so then once we understand what the strongly connected components are, okay, so I can look at the corresponding partition, the one that's here at the bottom. And the nice thing, why am I doing all of this work? Well, because we can show that exactly this partition is in the strict core. Okay, so the demanding solution concept, the strict core, which is more demanding than the core, it's non-empty because our partition belongs to it, that we can show. Okay, so also maybe another question then, so we have existence, the question that you may ask, okay, is the strict core unique? Is there a unique element? The answer is no. Here's an example. I will not go over this, but in general there could be other strict core partitions apart from our partition. Now, an interesting thing is that this is not a super good example, but in general, so you see the blue one, that's ours, that comes from, there's a unique strongly connected component, everyone is connected in this example, but then there's another one, this red one, where the agents break up in smaller coalitions. It turns out that a partition is core stable, then necessarily it's either our partition or it's a refinement. In other words, coalitions are broken up in smaller coalitions. So what cannot happen is that a core stable partition is obtained by mixing agents from one coalition and some other coalition from our SCC partition. The only thing that can happen is that you break up the coalitions into smaller coalitions, like you see here in this example, where 1, 2 split off from 1 to 3, and 3 is on its own. Okay? So this is an important result for our theorem, for the proof. But let's not go into this. What I would like to do is actually move to the second part of the paper, which is about strategy-proofness. So so the idea is to look at mechanisms which are systematic ways to assign partitions to problems, to hedonic coalition formation problems. We are still in the domain of friend-oriented preferences, right? And what I want to do is study these mechanisms, and okay, this is just pure notation. So this phi is a mechanism, phi I is the coalition of agent I, right? And a mechanism is core stable, individual rational, periodic optimal, if it always systematically assigns a partition that is core stable, individual rational, periodic efficient. Okay, so there's actually nothing here on this slide. It's just notation and some obvious definition of mechanisms. Okay, so now what I want to do is I want to look at strategy-proofness. Why do I want to look at strategy-proofness? So I can come up with several reasons. One reason is that it makes life easy for agents. So strategy-proofness says that there's no incentives to lie about your preferences. So if I have agent I, then if I tell a lie, so the squiggle I prime, then the mechanism will not give me something strictly better. The best thing I can do is just tell the truth to the mechanism. I don't have to worry about strategizing, complicated calculations or thinking about what other people could do or not. I just submit my true preferences and then I get the best possible outcome. Second thing, so it makes life easy. And second thing, maybe also it's a sort of a fairness notion, because it levels the playing field for all agents. It could be the case, so this is just another completely different situation, but if you think of school choice mechanisms where children have to be assigned to public schools, if parents have to submit their preferences, then a fairness property would be to have that everyone has the same sort of incentives, and we do not complicate life for some parents. One can think of situations in which some parents are more sophisticated or understand better the mechanism, and if it doesn't satisfy strategy-proofness, these parents have an edge over the other parents because they may be able to find out the good strategies, whereas other parents, less sophisticated, may not be able to do this. So if we have strategy-proofness, we don't have to worry whether sophisticated parents, will have an advantage or not. We know that everyone can simply submit their true preferences. No one has to worry about calculating anything. Now, a more general notion is group strategy-proofness, okay, which says basically that there's no subset of agents that can manipulate and be better off. Okay, there's different definitions. Let's use this standard one here. So what we want to avoid is all agents are weakly better off, and in the coalition, and one strictly better off. Then, okay, so why am I doing this definition? Well, you see it coming. What we have, our result, our mechanism, which we call the phi SCC mechanism, which assigns the SCC partition to every problem. It's strictly core stable, that we saw some minutes ago, but actually we can also show it's group strategy proof. Okay, so it has this strong incentive compatibility property. Then there's this nice proof that we skip. Then, an important question that we have to ask, well, right, you found some mechanism, but maybe there's many more that satisfy the same properties, right? Okay, so one question here is whether it's the unique one, and the answer is yes, sort of yes. Okay, what we have to exclude is, so we look at subdomains of our preference domain, or we look, or we can look at the whole domain of friend-oriented preferences. But what we have to make sure is that the domain is large enough. If I look just at a very small preference subdomain of our preferences, then very weird things can happen. So what we want to have is some richness, so that the result makes sense, and also we're not talking about completely irrelevant small domain. So what we do is we look at this richness condition, which basically says for any the preference domain should be as follows. For any agent I should be able to find in the domain some preferences such that any given set S can be the set of friends. So give me a set S. I know there's some preference relation in the domain for which this set S is exactly the set of friends. Okay, so I have to have certain richness. Now, if we have this, then we can show that a mechanism is core stable and strategy proof if and only if it coincides with our mechanism. So, to sum up, our mechanism satisfies strict core stability and it satisfies group strategy proofness, and we have this characterization that shows that it's in fact the unique mechanism that satisfies the slightly weaker properties of core stability and individual strategy proofness. Okay, so my time is sort of up. The presentation could continue, but these are let's say the main results. So I prefer to stop here. If there's any questions, I'm happy to answer, especially with respect to the domain also.
No, I was thinking that in a possible extension. I am not an expert in this topic. Now you have these preferences, no, and the output is a partition, no. You have a set of players. Each player has preferences, no.
Yeah.
And the outcome is a partition, no,
yeah.
of the set N. And a possibility is that players can cooperate, and then the outcome could be a balanced collection, right? So yeah, I can collaborate with you and with Cory.
Yeah. So basically, yeah, what you're saying is, okay, what about situations in which is natural? So if you think of the co-author situation, is I can work with Paco, but at the same time I can work on another project with Bettina, right?
Yeah,
so
exactly.
yes, that's a potential extension. We haven't thought of that extension, so I'm not sure what could happen. Yeah, so there's not. Yeah, I'm afraid I do not have too much to say about it, but yeah, maybe one can obtain some results. So yeah, there's another question.
Yeah, so I arrived a bit late, so maybe I missed it at the beginning. But what's the concrete criteria that leads individuals to categorize each other as friends or enemies?
Well, so could be if I want to work on a project with people, I could classify them as productive or unproductive, or clever or not so clever. I don't know. So the terminology friend enemy, it's not nice, but but basically we are referring to, let's say, think of productivity.
But then if it's productivity,
Yeah.
when you have this network connected to
Yeah.
friends and pointing to
Yeah.
friends,
Yeah.
if it's productivity and
Yeah, but productivity for me may mean something different than productivity for Paco, right?
so the criteria to categorize friends and enemies is not exactly the same for all individuals.
No. Everyone has. So for me, certain persons are productive and others are unproductive. But I know some of these unproductive people are actually very productive, but would not be, for working with me, it would not be, because they have lots of knowledge about other topics, or they are very good at certain things, but maybe not at others. So all of us have potentially different classification of enemies and friends. Okay, there's not a common classification. So that's very important.
And then I have another question.
Yeah.
So when you establish these core coalitions and the circles that you show us,
Yeah. Ups. Yeah.
Here.
Yeah.
It's on 9, 10, 11, right here. Okay, no, nothing. I thought that 2, 5, and 8 were also.
No.
It's not because
No.
it's only. Okay, yeah.
There is not a path, no, to connect.
No. So maybe then, if I have just 1 minute, let me just finish by saying that we, unless there's other questions, let me just finish by saying, okay, there's more results here, and we looked also, last week we worked very hard on an extension I cannot talk about really, but maybe it's interesting to mention extension. So one thing would be, this condition that I said I don't like too much is, adding a friend, even if there's many enemies, is good, right? This is an assumption we make. Now let's weaken this and say adding only a friend is good, right? So then it's symmetric. So we have condition E from our domain, and we have F bar instead of F, okay? Then if you do this, it sounds very, better, less stringent. Then we have an example here. It's actually super simple. Once you have found it, of course, that shows, so here you have a table, and these preferences satisfy E and F bar, and we show here, we can easily see that the core is empty. So even, not just a strict core, no, the core is empty. So in other words, if you change this condition, if you weaken it, okay, well, sounds good to me, but then, as with lots of domains that happen, that are studied in this literature, if you extend it, then the core can be empty, can turn out to be empty. Another idea would be to swap so instead of friend-oriented, I have enemy-oriented preferences. So in other words, first I had adding only an enemy is bad. Now let's do this. Adding only a friend is good, and then swap the second condition by saying adding an enemy, even if I add friends, it's bad. Okay, so I switch the roles of friends and enemies. Now if I do this, then you might say, oh, probably the similar results will come out. Surprisingly, the example that I just showed, this one, again, is valid. It satisfies these new conditions, these enemy-oriented preferences, and as we already saw, the core is empty. So, if I make these changes that seem, natural, then I turn into problems that the core becomes empty. Now, the last extension I will not talk about is to say, well, listen, instead of friends and enemies, I actually have 3 sets. So I partition all other agents into 3 sets, namely friends, enemies, and then there's some guys, I don't care too much about. They are not a nuisance, they are also not productive, they are just around in the room. maybe they prepare coffee or something. Fine, they can be there. Okay, so then there's, I call them neutrals. So this condition n there. If I add them to a coalition, you know, it doesn't make it worse, doesn't make it better, and then, you know, I can, and there we obtain some results, but I have to stop. I really have to stop here. So this is the last extension that we looked at. Okay, so okay, yeah.
This relation is present. For instance, if we had an enemy, this is bad. If we had a friend, is good. But if you change the order in which a friend or an enemy belongs to the coalition,
no, but
if you add an enemy is bad and then add a friend, then this is good. Or?
No, but yeah, but this is just a description of how I compare coalitions, but it's not. There's no real sequence, right? So. It's not dependent on the sequence in which. So if I look at coalition S, no, it doesn't depend on the order. Because if I look, you know, being on my own, and then I compare this with a coalition in which I have one enemy and one friend. You know, I just compare basically. You know, I can do this in steps, but it doesn't matter how I do the sequence.
And could you have like a bound in terms of the number of enemies? Because you say you have a new friend that comes together with enemies, it's always going to be better because I have a friend. But if it comes with 1 million enemies, it's probably not so good.
Right? Yeah. That's let's say a problem of our setting. Indeed, even if you come with 1 million enemies. Well, I don't know what kind of situation that would be, but in simple situations where we have coalition formation, the ones that I mentioned, maybe that's not very likely, but still it's a problematic feature of our domain. We do not have a restriction.
An extension where you have like a bound in terms of the number of enemies.
Yeah, that you can have. Probably, if you really insist, and if you give me a time, I think I will be able to find a counterexample where the core is again empty. Okay, so as soon as you start changing some things of the domain that we all agree look, you know, very strong conditions, as soon as we start doing that, it's quite likely, given, you know, what I've seen and the examples that we have constructed already, that this leads to an empty core. And that, in that case, you know, the issue is, okay, what do we do now? Because this last extension, we do have the strict core is empty, but the core we can show is non-empty. So in that case, I can still continue my research and I can still look into that. But as soon as the core is empty, and the core, in this case, for me, my interpretation, you know, in general, the core is quite large. If it's empty, then yeah, I have no really good idea how to proceed. So yeah, that's bad news. Yeah.
Okay. Thank you very much.
Thank you.